Hello everyone, I'm Dr. Daniel Barth with Astronomy for Educators. Today we're going to take on a very simple project, but an interesting question. What shape is the moon? Now, we've all heard flat earth silliness and maybe we've been asked this question by students sometimes, but let's take the moon. It's a little bit more removed. What shape is the moon? Now, if you ask someone, their first answer is, well, it's round. I go, okay, like a plate or like a ball? They think about it, oh, it's like a ball. Well, then the very interesting scientific question comes up, how do you know the moon is round? And many people will bluster or falter, but if you press them, the answers come down to one of two things. I've been told, or I've read it somewhere. Today's modern equivalent might be, well, I saw it on the internet. But in fact, that doesn't answer the question of how we know. If we've just been told something, we don't really know, we believe. Science has no place for belief. Science is based on data and evidence. So today we're going to look at a very simple evidence-based activity that you can use in your classroom to demonstrate and in fact help your students discover that the moon is indeed round. We're going to start out with a piece of nylon webbing. This is common webbing like you might see on a strap. You can purchase some at a home improvement store or a fabric store very inexpensively. You'll also notice that I've cleverly glued a series of about 7 quarters super glued onto this nylon webbing. Now you don't have to use quarters. You can use any sort of coin, poker chip, bottle cap. Steel washer would work just fine. And I've carefully glued these. And I've used a series of 7 because that makes one the very center and the others fade away around. Now the other thing we're going to use today is a rubber ball similar to what you'd find on a playground at any school and a binder clip. Now what we're going to do is we're going to take a look and say, gee, if we were looking at craters, what would we notice if we looked at them on the moon? Well, we would expect as we look on the moon's surface and we look around towards the limb, we're no longer looking at the craters straight on. Take a look, here's a round object. If we look at it straight on, indeed it does look circular, but the more tilted that it becomes, the more elliptical the surface appears. Well, let's take a look, and I'm hoping you can follow this. I'm going to try to do this the best I can on camera here. We're going to go ahead and wrap this around. And I'm going to use my binder clip. I'm a little off camera here, sorry. I'm going to use my binder clip to secure this strap. Now you could use Velcro, and Velcro in fact might be easier, but I've never had good luck with Velcro. It tends to come unstuck at the wrong moment all the time. Oh dear, here we go. Fiddling with the binder clip here. And we get it attached. There we go. I've just gone ahead and attached the binder clip. Now we bring it around and we look and we see that, oh golly, here we go. We have the quarters and they are glued around in the circle. And what do we notice? Well, when we're looking at one dead center on right here, it looks very circular. But as we move around to the edge in either direction as we progress towards the moon's limb, we see that the quarters appear more elliptical in shape. They're always round, the metal isn't changing, of course, just the angle at which we view them. And it doesn't matter how we turn the ball, we always find that as these come into view around the corner, that we see that in fact they appear more elliptical as they get towards the moon's edge. Okay, well, fine. We've had this interesting little demonstration, but what does it in fact mean for the purpose of viewing our moon out in space with a binocular or a small telescope? Well, if we take a look at this and we say, oh, okay, they look more elliptical, but if we start to analyze it a little bit, and I've got a small circle here. I cheated. I took an inexpensive wall clock and I drew a circle and used the hour positions. We have 2 o'clock, we have 5 o'clock, 7 o'clock, 9 o'clock, 12 o'clock, and drew all these nice little radiuses through the center. And here I've drawn exactly what we saw with the ball and the quarters on the nylon strap. As we move towards the edge, the craters become more elliptical. Now, this is hand drawn, obviously, and you might say, well, are all craters round? In fact, NASA studies indicate that uh, about 95% or more of craters are indeed round. That when an asteroid collides with an airless body like the moon, it tends to make a perfectly round crater unless it's at a very, very low angle, skimming along maybe 5 or 6 degrees above the horizon. Well, the other interesting thing we notice is that the way we've drawn these, and this goes back to what we saw with the ball, we took a look and effectively the little nylon strap here serves as a diameter line. And we notice that no matter how we turn this, the elliptical craters are always perfectly aligned with that lovely nylon strap. Well, we look at it here and we find that what's actually true is that these crater axes, the long axis of the crater is always perpendicular to the radius line that passes through it. So when we draw these, we get two interesting things, two interesting ideas. Now, this is an hypothesis at this point. We haven't proved anything. We're just working with a model that is both physical and mathematical, and essentially we come up with two ideas. The first, that craters always appear more elliptical as they get further from the center of the moon's disk. The second thing that we've noticed is that the long axis of an elliptical crater is always perpendicular to a radius line drawn through the center of that crater. So we take a look at these two ideas. Here's our hypothesis that's developed from our very simple model: rubber balls, some nylon strapping, and a few circular round quarters. And we get these two predictions. Our model is basically making predictions. Keep in mind that any physical model is basically a hypothesis made flesh, if you will. We are taking the hypothesis and we're creating a model. This is a hypothesis in physical form, and then we went ahead and we formalized the sketch. And then what does the sketch tell us? These are two predictions that our model makes. Now the question comes, can we indeed observe this and find out that it is true? In fact, any very small telescope, we're all familiar with the very inexpensive department store telescopes that seem to pop up around Christmas time. They're often available very inexpensively at garage sales on eBay, etc. If you ask around in your classes, you're undoubtedly likely to find one or two students who say, oh yes, I have one of those. Do you use it regularly? Have you discovered anything with it? Well, no. Okay, well you should. Take that small telescope and a gathering of students out in the school parking lot. It doesn't have to be anywhere particularly dark because the moon is so bright. And if the telescope can magnify to about 50, between 50 and 100 power, you can absolutely confirm this hypothesis. When you observe, you will find that craters that are closer to the edge of the moon do in fact appear more elliptical everywhere across the moon's surface, and that craters that are towards the center are almost perfectly circular in shape. Now, do you have to have a telescope? No, you do not. There are millions, I'm sure, of photographs of the moon that are on the internet. If you go into Google, Yahoo, Bing, your favorite search engine, and say image, high resolution image of the moon, or image of the quarter moon, image of the crescent moon, image of the gibbous moon. This works best. You can most easily see the shape of the craters if you look along the terminator, the line that separates the bright portion of the moon from the dark, the line that separates daylight from darkness. That has the lowest angle of the sun, and it shows off the shape of the craters very easily. You will find that in every photograph you take a look, that these two things are in fact true. Your students will discover that yes, craters towards the center of the moon are circular, and that as you look at craters closer to the moon's edge, they are more elliptical. Furthermore, if you take and you look at these photographs, especially if you have the ability to project them up onto a screen or whiteboard in your classroom, you can easily put up a meter stick and you can observe that in fact the long axis of the crater is always perpendicular to a radius line drawn through it. Now, of course, every once in a while somebody comes up and says, well, yeah, of course, but does this prove that the moon is in fact round and spherical like a ball? Science doesn't deal with proof. Mathematics does. Science does not. Science deals with data. So when we look at this and we have, again, I'm going to use our sketch here. When we look at this and we find that we view many photographs of the moon and we find this pattern of more elliptical towards the edge, more circular towards the center, and that the long axis is always perpendicular to a radius line drawn through the crater. What we find is that when we look through this, we find that yes, this model fits virtually all craters on the moon. And could it have been manipulated? Could someone have gone up and dug all those craters by hand? Well, the idea becomes really quite silly. And someone else might ask, well, what's the chance that this came out strictly by random chance? Perhaps there were very low angle craters that were always on the moon, but again, if that were the case, we would expect these very elliptical low angle impact craters to be randomized in all directions. There's no physical reason why they should remain perfectly perpendicular in their long axis to a radius line drawn through them. And so what we have found is that in fact the moon is round, and with any small telescope or with even just photographs of the moon, we can cull from the internet, we can use a few simple materials, we can create a model, students can derive a written hypothesis from it and then confirm it by experiment. This discovery-oriented approach to proving the moon is round is very popular and very powerful. It keeps hands and minds engaged, and discovery is in fact ownership. We want students to take ownership of what we teach them, and the discovery methodology does that better than anything else. Better than any video you can find, better than any worksheet you could possibly write. Having students discover scientific ideas on their own is indeed a powerful methodology that you can use in your classroom. If you have questions, if you've liked this video, all of these things are, many of them are found and they're all based on ideas in the Astronomy for Educators program that I run at the University of Arkansas. The Astronomy for Educators materials, if you wish curriculum guides and other things, you can write to me, Dr. Daniel Barth at astronomyforeducators@gmail.com. If you would like a copy of the Astronomy for Educators text, that's available free, scholarworks.uark.edu/OER/2, and that will let you download the entire Astronomy for Educators text for free. It's published by the University of Arkansas Library Press. And many of these things, these ideas, are featured in a regular program that I have on the internet, How Do You Know? Mondays at 4 p.m., explorescientific.com/howdoyouknow. And you can find older videos on the Astronomy for Educators page on Facebook. I'm Dr. Daniel Barth. Thank you for watching.